All right, here we go. Welcome to physics video 2.2.5. So we're going to kind of continue our super quick crash course in calculus, but this time we're going to focus on an integral. All right, so here's the deal. So in video 2.1.5, we focused on derivatives, right? And what we learned was that when you take the derivative of a function, it gives you the slope. All right? The integral is going the opposite way. When you do an integral, you're asking yourself, what function would have this function as a derivative? Okay? So, for example, if I tell you that f of x is, I don't know, we'll do, let's say, 6x squared minus 2x, right? Then the derivative of f with respect to x is this new function, right? Which I can get using the power rule, right? So let's say I'm going to go 2 times 6 is 12x, and then I decrease my power by 1, right? Remember, when you take a derivative, you decrease your power. So that's 12x to the first, which you can just write as 12x, minus, let's see, this is x to the first, so 1 times 2 is 2 times x to the 0 is just that, right? Okay? So, going this way is taking a derivative. All right? Now, taking an integral, you're going the opposite way. So taking an integral, what we would do is we'd say, all right, f of x is 12x minus 2. All right, and when you take the integral, it gives you the integral of f of x. Notice the notation here, because I shouldn't have done that so quickly, right? So integral. So to make an integral symbol, it's sort of like a long stretched out lowercase, well, any case letter s, but it's a long stretched out s. So that symbol that I just drew there is the symbol for integral. It is meant to be tall. So the integral of f of x with respect to x. So notice this variable will match whatever's on your horizontal axis, is whatever thing I took the derivative of to get this. So over here, the derivative of 6x squared minus 2x gave us this. So now taking the integral goes the other way. 6x squared minus 2x. Okay? So, derivative, this is what we were working on before. Integral just goes the other way. All right? Now, unfortunately, it's not quite that easy, because as we're going to see, it turns out that this is not the only answer to this. Okay? And the reason for that is this. What's the derivative of a constant? So what's the derivative of, I don't know, 5? Oh, well, that's just 0, right? So I could tack on a plus 5 here, just like I could tack on a plus 5 over here, and that wouldn't change the derivative, right? Okay, so that's sort of what's going to be at the crux of what makes integrals a little bit more confusing than derivatives, okay? So, let's get all of this into words that are going to be useful to you, all right? So, let's do this. Where's my shade? Hiya. All right, so here we go. So this is video 2.1.5, is this, 2.1.5. Given a function f of x, the derivative, and I'm going to use math notation here for a minute, f prime of x, the derivative, f prime of x, gives, sorry I missed my s there, gives the slope of the function at any given point. All right, and the notation we use is this. The derivative with respect to x of f of x is, we call it math, f prime of x, and it's the slope of f of x, right? Okay, so that's what a derivative is. All right, now, given a function f of x, so we're going to have, once again, a function f of x, the integral of that function, also known as the antiderivative of that function, it's some new function, which we're going to call capital F of x, whose derivative is f of x. All right, so when I take the integral of this, when I take the integral of little f of x, I'm looking for a new function, capital F of x, where if I take the derivative of capital F of x, I get my original little f of x. Okay? And the notation we use is this, all right? And I'm going to actually start here in the middle, all right? So when I take the integral of little f of x, I'm looking for some function capital F of x, where if I take the derivative, I get my little f of x, all right? And the notation I use is this. The integral of f of x with respect to x is capital F of x, okay? So our goal is we want the derivative of capital F of x to equal our original little f of x, okay? The problem, like I said, and I'll show you this here in an example, the problem is that there are a bunch of solutions, all right? So doing it this way, just taking a straight integral, is actually what's called an indefinite integral. It's indefinite because we haven't sort of figured out exactly what the answer is. We've just sort of narrowed it down to one of, well, no, an infinite number of infinitely many solutions, all right? So here, this is the super important thing, all right? The only time, especially in physics, the only time you're going to use an indefinite integral is if you know at least one point on your capital F of x, okay? So you're going to take your integral, that's going to give you some new function, f of x. And then to figure out exactly what the function is, you have to know at least one point on that answer function, okay? All right, now if that's not the case, then we use what's called a definite integral, all right? So to take a definite integral, what it does is, instead of taking an integral and getting your new function, what it actually gives you, oh, what just happened? My smartboard got dumb. All right, so instead of it giving us the new function, it just tells us how much the new function changes between two specific points. I wish I had written two specific values of x, okay? And so the way that we write this is this. Instead of, I'm covering up stuff with my hands, you can't see what I'm doing. Instead of just writing this as our integral, we add in our starting and ending values of x, okay? So notice the notation here. Let's see if I can get these both to fit on the screen at once. Let's clear off our ink. Okay, so when we did, an indefinite integral, I used this notation, right? For a definite integral, I use this notation, and I add in these two bounds. I say, all right, I want to know what the integral is between some starting value of x and some ending value of x. And instead of that giving me the function, it gives me the change in the value of the function between those 2 points. All right? But again, you've still got that same relationship, that the derivative of your capital F of x is f of x. All right? So it turns out, and I'll show you this here in an example, it turns out when you take a definite integral, in addition to giving you this, the change in f of x, it also gives us what's called the area under f of x between your two x values. Okay? So I think probably the easiest way to do this is to just kind of dive in. All right, so let's start with a real simple example. All right, so suppose I give you this. So here's x, here's f of x, all right? So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And then f of x, 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so f of x is 4. So let's just draw this. So there it is. 4 f of x. All right, now suppose I wanted to find the integral of f of x. All right, so because this is an indefinite integral, I'll try to draw it in red. All right, I will actually. All right, so let's find the integral of f of x with respect to x, right? Okay, so really what I'm looking for some new function, capital F of x, such that the derivative with respect to x of capital F is my original function, 4, right? But remember, So what this is saying is the derivative everywhere is 4. And remember, the derivative is just the slope, right, of the function you're taking the derivative of. So I need to find a function that has a slope of 4 everywhere. Oh, well, y equals mx plus b, right? Or for us, f of x equals 4x plus some y-intercept, all right? Now, in calculus, this b might not necessarily be the y-intercept. It happens to be here, but we don't know what it is, okay? So I'm going to put a little placeholder, c, all right? And in calculus, this is what you'll usually use, is c, all right? So, oh, shoot, this is supposed to be capital F, right? Because that's what we were trying to find. So that is a capital F, all right? So just note, if I take the derivative with respect to x of capital F, that's the derivative of capital X, the derivative with respect to x of capital F. Okay, well, what's the derivative of 4x? Oh, well, that's just 4. What's the derivative of a constant? 0. Oh, 4 plus 0, that's 4, okay? So that's why this is the integral of, let's do this. Let's move this so we can see a little more of this thing. So that's why this is the integral of this. Because if you take the derivative of this, it gives you the original function, right? Okay. Now, the other way we could have done this, notice I kind of did this conceptually. I said, oh, well, it's got to be the slope, right? And then I went to geometry and used the equation of a line, right? Now, the way that a mathematician would do this is they would say, all right, let's just do this. All right, so the way a mathematician would do it is they would say this. All right, so f of x is 4. I want the integral of f of x with respect to x. That's the same as the integral of 4 with respect to x. And then you'd ask yourself, all right, well, what thing can I take the derivative of to get 4? Well, 4 is the same as 4 times x to the 0, right? Because remember, x to the 0 is just 1. All right, and remember, when you take the derivative of a power, you use the power rule, right? And so that decreases your exponent by 1. So going backwards, if we ended up at 0 after decreasing by 1, this must have been x to the positive 1. So this is 4x to the 1. Does that work? Let's see. The derivative of 4x to the 1, multiplied by 1, that gives you 4x. Yes, it all works, right? Okay, so, oh no. So we get 4x, but then there could be some other constant, right? There's no reason why there couldn't be some constant added on here. Okay? So there's my derivative, or my integral. So that's my capital F of x. Okay? Now, to figure out what c is, I would have to give you I would have to give you at least 1 point on the graph of x. Okay? So maybe the problem would say this. Maybe the problem would say, suppose little f of x equals 4. If the derivative of capital F of x, with respect to x is f of x, and f of, 3 is, say, 5, then find f of x, right? Capital F, okay? Sorry, it'd be better about my, if you guys are picking up on the difference between my capital F's and my lowercase f's. All right? So, well, so this statement right here is the same as saying that the integral of f of x with respect to x is capital F of x, right? So we already did this, right? Remember we got 4x plus c equals f of x. We just did that a minute ago, right? Okay. Well, so now what I'm going to do is I'm going to combine this information with this information, right? So let's see, I'm going to plug in 3 for x. So 4 times 3 plus c equals f of 3, capital F of 3, which is 5. 12 plus c equals 5. Subtract 12 from both sides. C is negative 12. No, it isn't. Sorry, subtract 12 from both sides. And c is negative 7. So that means capital F of x is what? 4x minus 7. Okay? All right. Now, suppose that I hadn't told you this. Suppose I had not told you the coordinate of one point. All right? Then all we could do is this. We could take what's called a definite integral. All right? So here's how that would be set up. So the definite integral allows us to find a change. Okay? So, same example. Suppose f of x is 4. All right? If the derivative of capital F of x equals f of x, then find, let's do this. Let's find capital F of 7 minus capital F of 2, how about? Okay? So, let's think about this. So, notationally speaking, this is a definite integral. All right? So, what we're looking for here is the integral between two values of x, right? So we want x to go from 2 to 7 for a function f of x with respect to x, right? So this is the integral between 2 and 7 of, remember, f of x is just 4. So 4 with respect to x. All right, and so the way that you write this is, what you do is you take the integral of this mess, and you don't worry about the c. All right, this is now, to be clear, this is now we're doing a definite integral. Because notice I'm looking for the change in the value of my function, right? And so that tells us it's a definite integral, okay? So, what thing can I take the derivative of to get 4? Oh, well, that's 4x, right? And don't worry about the c. Do you know what? Better yet, I'm going to put the c in, all right? But in a minute, you're going to see that it doesn't matter, okay? So that's my derivative, all right? So after this time, and you might want to make a note of this, after this one example that I'm doing right now, I'm never going to, when I use a definite integral, I'm not going to use c. So no c for definite integrals. And this example here will show you why. All right, so this is my capital F of x, all right? And then the notation you use is you say, all right, we want to evaluate it at 7 and 2, and then find the difference, okay? So basically what we're doing is we're finding f of 7 minus f of 2, right? Okay, so I'm going to plug 7 in here, and I'm going to plug 2 in here, and I'm going to subtract. So if I plug 7 in, look what I get. I get 4 times 7 plus c. So that's if I put 7 in, minus 4 times 2 plus c. And notice, this is what I was just saying, the plus c's cancel, don't they? All right, so now I get 4 times 7, which is 28, minus 4 times 2, which is 8. 28 minus 8 gives us 20. Okay, so that's my change in f between those two values of x that I chose, right? Okay, I got 20. All right, so that is what's called a definite integral. And it's nice because it just gives you a numeric answer, right? Okay, and you don't need to worry about the c, which is another added bonus, all right? I will tell you, in physics, we almost always use definite integrals. Okay, so let me show you what this all means. So what we just got, we just found that the integral between 2 and 7 was 20. Let's graph this thing. All right, let's do this. All right, so here's x, here's f of x. 1, 2, 3, 4. All right, and then our x value goes 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7. All right, so you might remember, maybe, I know there's been a lot in this video, so maybe you don't remember this. Let me highlight it again because it's super duper crazy, mega, colossally important. This. A definite integral gives us the area under f of x between x final and x initial. All right? So what that means is this. Look, in this example, here was my x initial, here was my x final. So if you think of this, we're going to find the area under the curve. So here's my curve, right? This is f of x equals 4. I just drew that in that weird orange color. Okay. 2 is my x initial, 7 is my x final. What's the area of this little rectangle that I just drew out? Well, it's got a height of 4 and a width of, what's the difference between 2 and 7? See, that's 5, right? From 2 to 7 is 5. How do you find the area of a rectangle? 4 times 5 is 20. All right, this will come up a lot where you'll be given a graph and asked to find an integral. All right, to find the integral, well, the definite integral, I guess, you're simply finding the area under the curve. All right, so there we go. That was one example, and we're at 22 minutes. Okay, so there's a lot of concepts there. All right, so let's see if we can do this now, but with maybe a slightly tougher example, okay? A little bit tougher, all right? So now we've got this, f of x equals 4x, okay? So we'll do two types of problems here. Example 1, f of x equals 4x. All right, so suppose I tell you that the derivative of capital F with respect to x is little f of x, and f of 2 is, I don't know, how about 24? Okay, so let's find capital F of x. All right, so this is example number 1 here for this deal. So I guess example A, whatever. Okay, so remember, anytime you know this, if you know the derivative of a thing is another thing, and you're trying to find the derivative of the first, anytime you know the derivative of a thing is another thing, and you're trying to find the thing, that's a sign that you take an integral, okay? So, wow. So we want to do this. So we want, so what we know is our thing, f of x, is the integral of f of x with respect to x. So that's the integral of 4x with respect to x. So right now my exponent is 1. So what thing would I take the derivative of to get an exponent of 1? Well, it's got to be x squared, right? Okay, because when you take your derivative, it's going to decrease by 1. So now the question is, when I take the derivative of this, how am I going to end up with 4? Well, so it's, let's see, 2 times what is 4? Oh, this has got to be 2, right? Because then when I take the derivative, I'm going to have 2 times 2, that'll give me 4. Decrease the exponent by 1, that gives you 1. All right? So you get 2x squared plus c. Okay, so that's what capital F of x is. This is an indefinite integral. All right? So now what I can do is I can use the fact that I know that f of 2 is 24 and solve this thing. So let's see, f of 2 is 24. So that means that 2 times 2 squared plus c is 24. So 2 times 2, 2 squared is 4 times 2, so 8 plus c is 24. It looks like c is 16. So f of x is 2x squared plus 16. And notice, if I take the derivative of this, I do, in fact, get 4x. Okay? So that's one example. That was an indefinite integral. All right, let's do a definite integral. All right? So we're going to start out with the same terminology. If the derivative of f with respect to x is little f of x, find, let's do f of, I don't know, how about 5 minus f of 2. Okay? So what we're looking for here is this. F of 5 minus f of 2, these are all capital F's, is the same as the integral from 2 to 5 of f of x with respect to x. That's the same as the integral from 2 to 5 of 4x with respect to x. All right? So now notice we're doing a definite integral here because we know our bounds, right? We're looking for a change in f. So that's a definite integral. We know the bounds. Okay? So I don't need to worry about my c. So what thing can I take the derivative of to get 4x? Oh, we decided that was 2x squared, right? Exactly like we just did a minute ago. But now I got to set my endpoints, and I want to evaluate that between 2 and 5. Okay, so notice when you do this, this expression has an integral, right? There's an integral over here. I've already taken my integral, so I replace the integral with this weird little bar here, and that just means evaluate it between 5 and 2. That's what that notation means. Okay? So what I'm going to do then is I'm just going to take, 5 and put it here. So 2 times 5 squared minus 2 times 2 squared. And so 2 times 5 squared is 50, minus 2 times 2 squared is 8. 50 minus 8 is 42. All right? There you go. Now, what does this represent? That represents the area under the curve, right? We just got 42. So let's see if that works. So we just found the area between 2 and 5, and we got 42, didn't we? Let's graph this and see what this looks like. See if we can figure out what's going on here. So, all right, so 0, 1, 2, 3, 4, 5, and then, so we'll go 4, 8, 12, 16, 20. Okay, that's a straight line. All right. Okay, so. All right, so what we just did is we found the integral between 2 and 5 of f of x with respect to x. So that ought to be the area under the curve between 2 and 5. So I want this area here. Okay? So what this represents is that area. All right? So take a second, use some algebra, geometry, and find that area. So I'm looking at it as, well, let's see, it's the area of a big rectangle, which I'm going to highlight in yellow. So it's the area of this yellow triangle, right? So it's all of this area minus this area, right? So the big yellow triangle yellow minus pink, right? So let's see, the yellow area, well, that's a triangle that is 5 by 20, right? So area is 1/2 base times height. So 1/2, 5 times 20. 5 times 20 is 100, half of that is 50. Minus this yellow triangle, right? So the yellow triangle has a base of 2 and a height of 8. So 1/2 base times height, 1/2 2 times 8. Half of 2 times 8 is, in fact, 8. Oh, except you can't see my 8. 8. 50 minus 8, 42. Holy cow. There we go. Same answer. High five yourself. Psh, sweet. All right. So, that's kind of the deal there. Those are really the different types of problems you need to know how to do. So, I'll tell you what. I've totally run over my limit here. So why don't you do this? Do 2 things for me. Oh, that's a terrible color. How about this? If the derivative of capital F with respect to x is f of x, for this f of x, I want you to A, find f of, I don't know, let's do f of capital 3, capital F of 3 minus f of, -1. What happens if you have a negative? No big deal. All right, and then B, let's suppose I tell you that capital F of 2 is, 6. Then see if you can find capital F of x as a function. All right, so I will stop there and we'll start class with this the next time I see you. You'll probably need to remind me because it's now June 12th. There's no way I'm going to remember this at the start of next year. Okay? There you go. You know what? I decided to just do it. So you can fast forward if you want, see if you get the right answer. Hopefully you tried it on your own already. All right, so here we go. So for A, we're trying to find f of 3 minus f of -1, capital F, right? So that's the same as the integral between -1 and 3 of little f of x with respect to x. So that's the integral between -1 and 3 of our original f of x, which is this. 4x squared minus 8x with respect to x. So now I just ask myself, what do I take the derivative of to get this thing? Well, what do I take the derivative of to get 4x squared? Well, it's going to be something x cubed, right? So let's try 4/3 x cubed, right? Minus, let's see, to get this, I need something x squared. So I think 4x squared, right? And then you want to evaluate this between -1 and 3. So I'm going to get 4/3 times 3 cubed minus 4 times 3 squared minus 4/3 times -1 cubed minus 4 times -1 squared. And solve it, right? So let's see. This is going to give you what? 36 minus 36? Really? Do you get that? Yeah, you do, don't you? Look at that. So that's all 0 minus, let's see, 4/3, so that's -4/3, right? Because -1 cubed gives you -1. -1 squared, so let's see, minus 4. So this is, what is that? 5 1/3. Alright, so there you go. So that's part A. Part B, same idea. So to do part B, we're going to go, all right, well, let's see. I know that f of x is the integral of f of x, dx. Notice, no bounds here, right? Because this is now an indefinite integral. So that's the integral of 4x squared minus 8x with respect to x. I guess I should put parentheses in here. So this is indefinite, so I do kind of the same thing I just did, right? What gives me that? So that's the 4/3 x cubed I just had, right? Minus 4x squared plus c. Now we got to solve for c by using this. So plug in 2. So you get 4/3 times 2 cubed minus 4 times 2 squared plus c equals 6. And solve it, right? So you get, let's see, 2 cubed is 8, times 4 is 32, over 3 is 10 2/3, minus 16, plus c equals 6. 22, so what's that give you? 11 1/3, I think. Because 10 2/3, 11 1/3, that gives you 22, minus 16 gives you 6. There you go. All right, yeah, so that means then that f of x is this. 4/3 x cubed minus 4x squared plus c, which is the 11 1/3. All right? So that is that. All right, now, I just blew some of your minds. Some of you are like, what's going on? You'll have all year to practice this on calculus. And I'll be honest with you, at this point in the course, I'm really more interested that you know, if for a given situation, I want you to know whether you should take a derivative, take a definite integral, or take an indefinite integral, if you're given the function. And if you're given a graph, you should know whether you're supposed to find the slope, or find the area, or whatever. Okay? So you're going to make mistakes taking integrals and derivatives at the beginning of the year here. You'll figure it out before the end of the year in your math class. All right? So, but this is the general idea. All right? There we go.